In this video, I'll be covering the concept of the optimal binary search tree, which can be solved using the dynamic programming. So within the dynamic programming, the problems that can be solved are, that is, 0 or 1 knapsack problem, unlike in the case of the greedy approach. That is, using the greedy approach, the fractional knapsack is being implemented. That is, a portions of the items or can be taken into the solution set. And coming to the 0 or 1 knapsack, which can be implemented using the dynamic programming, that is, either you can take that kind of the item or drop that kind of the item using the dynamic programming. In the same fashion, that is, we can also solve the problem of the optimal binary search tree using the dynamic programming. So what is actually the optimal binary search tree, and what is actually the solution related to the optimal binary search tree using the tabular method will be discussed in this particular video. So in the optimal binary search tree, each node is assigned a weight that represents the probability of key being searched for. That is, you are familiar about the binary search tree. That is, binary search tree has certain properties which we can say, like the root node should, and similarly there are left child and the right child, and the left subtree should be less than the root node, and the right subtree should be greater than the root node. So in the optimal binary search tree, every node is being assigned, that is, every node, or we can also say the key, is being assigned with the weight. And what is this weight? That will be discussed in your next part. That is, optimal binary search tree is a variant of the binary search tree where the arrangements of the nodes is strategically optimized to minimize the cost of the searches. What does it mean? That is, given certain kind of the keys. The keys can be either alphabets or numerical values like 10, 20, 30, 40. Given certain kind of the keys, and also you're being provided with the probability of successful search and the unsuccessful search. Initially, consider the keys are being provided like A, B, A, B, C, D, E, and the probability of successful searches is also being provided. Consider the probability of search of A to be equal to something like 0.1 and B to be equal to something like 0.3 and so on. So what is actually the problem of optimal binary search trees? Given certain kind of the keys and given certain kind of the weights, then you have to arrange these keys in such a way that whenever you find the most frequently searched item, this item should be placed close to the root. That is, the key idea behind the optimal binary search tree is to place frequently accessed items close to the root, and whereby it reduces the search time. That is, whenever you need to search for a particular key, and having this kind of the key with the most highest probability of searching, that key has to be kept close to the root, because when you are finding any kind of the element within the binary search tree, first you'll be searching from the root. That is, you'll be searching from the root, and then traverse accordingly towards to the left subtree or towards to the right subtree, depending upon the key that you are searching for and what is the value that has been present in the root. So whenever the most frequently accessed item is kept close to the root, then the cost that has been associated to search for such item will be minimized. And what is the contrary part? That is, if you place the most searchable or accessible item or the key somewhere at the leaf node, which is frequently accessed. Like, take for example, here if you consider the letters to be equal to A, B, that is, we have the keys to be equal to, that is, A, B, C, D, and similarly E, and assume E is the letter which is most frequently accessed. And in this scenario, if you place, like take for example A, B, and similarly C, and the next one that is D, and the next one that is equal to E. So when you are placing the most accessible item at somewhere in the leaf node or just below above the level, then in such cases, what happens when you search for the letter E? It has to search for the root, compare, and traverse accordingly. That is left subtree. B, it is not matched. D, it is not matched, and E is been matched. So the time that is been required to search for E is more. And what happens in the next scenario? Like take for example, E is being kept as an at the root level, and then something like your A and similarly B by maintaining the property of the binary search tree. And we have something like your C and something like your D. Consider, since the most frequently accessed element or the key E is being kept at the root, then the cost that has been required to search for this kind of here the item is very less as compared with this kind of here the optimal binary search tree arrangement. That is what the optimal binary search tree is being associated. So OBST, which is also known as the weighted balanced binary tree. So here the optimal binary search tree says, given the sequence k equal to k1 less than or k1 less than k2 less than etc till kn of n sorted keys, with the search probability pi for each kind of here the key ki. So where ki indicates the key and pi indicates the probability. The aim or the goal of this optimal binary search tree is to build a binary search tree with the minimum expected cost. You can arrange the elements of the binary search tree in different ways. And out of all these ways, what is the most optimal one? That is what the problem of optimal binary search tree is being indicated. So you should be familiar about how many number of binary search trees can be generated for n number of the items. That is given n number of the nodes, and in order to find how many number of binary search trees that can be generated is given by statement, that is BST of n equal to C of n, that is Catalan number, which is been given by 2n factorial divided by n plus 1 factorial into n factorial. So consider n equal to 3. What does this indicates? That is, there are 3 elements or 3 nodes which are present. When you consider n with the value to be equal to 3, there are 3 nodes. Then based upon the formula, like the Catalan number, you get that is 5. What does this indicates? When you take n is equal to 3, that is 3 nodes, then we can generate 5 such binary trees. 5 binary search trees can be generated. What are those 5? That is, we can arrange, assume like 3 nodes to be equal to 1, 2, and similarly 3. And here you can observe the 5 binary search trees are being generated. And you can take also the value of your the n to be equal to 2, n to be equal to 4, and so on. Replace the value of your n in the Catalan number, and you can generate how many such binary search trees can be generated. So when you consider n equal to 2, that is, if you need to find how many number of binary search trees can be generated, just replace the values of your the n in your Catalan number, and you get the value to be equal to 2. What does this indicates? When you are being provided with 2 nodes, consider the 2 nodes to be equal to, that is node 10 and similarly node 12. There are 2 nodes which are being present. And how many ways we can arrange these provided with these 2 keys? There are 2 binary search trees that can be generated. What are those 2 possibilities? That is, here place 10 as the root node and similarly 12 as the right child. And the next scenario, that is next binary search tree. This is your something like binary search tree 1 and binary search tree 2. So 2 binary search trees can be generated. You have to maintain the property of the binary search tree. So here you can have the root as 12 and the left child to be equal to 10. This is an introduction related to your binary search trees. And what is actually the optimal binary search tree? that is given certain kind of the keys. That is, consider A1 to be equal to 10, that is node 10, and similarly node 12. And there are also provided with the probabilities. Of course, the probability is being given as something like your 34 and 50. In the actual scenario, the total probability of successful search and unsuccessful search should be equal to 1. And for the simplicity, consider the probability to be equal to 34 and similarly 50. What does this indicates? That is, 50 has the highest one. That is, you need to search for the node 10, which has a probability to be equal to 34. And if you need to search for the node to be equal to 12, which has a probability to be equal to 50. And what is the objective of the optimal binary search tree? That is, the most frequently accessed item, whichever is highest one, that is 12, should be kept close to the root. That is what the optimal binary search tree has been indicated. So if you consider the possibilities of arranging these two elements, that is, we can arrange 12 as a root and the left child will be equal to 10, and we can arrange root node as 10 and the right child will be equal to, that is 12. Find the cost. So how to find the cost? Assume, this is your level 1 with the nodes, that is 12, and this is your level 2 with the node value, that is 10. So how to find the cost for this kind of the binary search tree one? That is cost equal to what is the cost of 12? That is cost of probability of searching 12, that is 50, because the probability of 10 is equal to 30 and similar 12 is equal to 50, the same thing. So here, according to this BST binary search tree one, you have placed 12 as a root node, which is present at your level 1. So 50, what does this 50 indicates? That is with the probability 50 into what is the level number. So level number is equal to 1. So 50 into 1 plus what is the probability of the node 10. So node 10 is equal to 34. So 34, and what is this level? So level is equal to 2. And if you calculate, that is 50 plus 68, that will be equal to 118. As I mentioned, we can also arrange this kind of the elements in another BST, that is BST2. And within the case of the binary search tree 2, that is, we are keeping the root node as 10 and the 12 as the right child. So what is the cost? As I mentioned, the cost of the root node, that is 10, that is equal to 34 into what is the level number. So level number will be equal to 1 plus what is the cost of the node 12, that is probability, that is 50 into what is the level. Level number is equal to 2. So if you compute this one, that is 134. So you got binary search tree with the cost to be equal to, that is 118, and there is also another binary search tree with the cost to be equal to 2, and binary search tree with the cost to be equal to 134. What is an optimal one? That is minimum. The minimum is equal to 118. So you have to arrange this kind of the problem with the keys 10 and 12 in such a way that 12 should be the root node and 10 should be the left child, provided with the probabilities 34 and 50. This is what we can say. This is the optimal solution. This is the solution for your optimal binary search tree for this kind of the problem. So consider the same thing, that is find the cost of the tree where the items of the probability are being given, A1 to be equal to 0.4, A2 to be equal to 0.6, and A3 to be equal to 0.3. In such cases, we can arrange the elements, that is A1, assume one of the binary search tree. That is, we have arranged A1, A2, and similarly A3 in this order. And similarly, this is the level 1, level 2, and similarly level 3. How to find the cost? That is, the cost is what is your probability of searching A1? Because A1 has been kept as a rule. The probability of searching A1 is equal to 0.4. And what is the level number? This is your level number. Level number, that is 1. So 1 into 0.4 plus what is your probability of the item 2? That is 0.3 into the level number, that is 2. And the third level, that is the probability of the third item is given as 0.3 and the level number is equal to 3. That will be equal to, that is 1.9. This is one of the binary, how to find the cost for the provided binary search tree with respect to keys and with respect to probability. Similarly, if you consider n equal to 3, that is there are 3 nodes. How many number of binary search trees can be generated? That is n equal to 3, that will be equal to 5. So these are the probable arrangements which is been left as an, this is only the additional part. These are the binary search trees which can be generated. So within your optimal binary search tree, given the keys, that is 10, 12, 20, and you'll be also provided with the probabilities. That is probability of searching 10 to be equal to some value, probability of 12 with some value, probability of 20 to be equal to some value. So out of these binary search trees, that is BST 1, 2, 3, 4, and similarly 5, how to find the optimal binary search tree? Whichever is the cost is minimum. Like if you compute the cost, as I mentioned in your previous slide, how to find the cost provided with the probabilities. So if this cost is minimum, then this will be the minimum optimal solution. Or if this is minimum, then this will be the optimal binary search tree solution. Now coming to the actual problem example, consider n equal to 4. That is, there are 4 keys which are present. That is A1, A2, A3, A4. With the keys names to be equal to do, if, int, and similarly while. And the next one, that is probabilities are being given, as well as the 2 kinds of the probabilities. So what does this P denotes? P denotes probability of successful search. And what does Q indicates? So Q indicates the probability of unsuccessful search or the failure. So P can be explained as the probability of successful search, and whereas Q explains about the probability of unsuccessful search. So here find the optimal binary search tree. That is, you need to find what is the optimal binary search tree for this kind of the problem. So the problem will be given related to the optimal binary search tree. That is, given the keys and number of keys. According to this example, there are 4 keys, and the keys are do, if, int, while. And you'll be also provided with the probability of successful search and the probability of unsuccessful search. So the probability of successful search is being given by the letter that is P, and the probability of unsuccessful search is being given by the letter that is Q. And you need to solve the problem of optimal binary search tree for this problem. So there are certain statements which are being used, the computation statements. That is W of I comma I equal to Q of I, C of I comma I equal to 0, and similarly R of I comma I equal to 0. So what does W indicates? W indicates the weight, and similarly the cost. And similarly here you can observe W of I comma I is equal to Q of I. And what does Q stands for? The probability of unsuccessful search. And similarly, when you need to find C of I comma J, where I is not equal to J, then in such cases, it is been given by C of I comma K minus 1 plus C of K comma J plus W of I comma J. And when the value of the I is not equal to J, when in finding the weights, that is W of Ij is given as P of J plus Q of J plus W of I comma J minus 1. These are the initial conditions or initial statements which are being used to find the optimal binary search tree. That is, W of I comma I is given as Q of I, where I is equal to I. J value is equal to I. But when I is not equal to J, then in such cases, it is been given by, that is, W of Ij is given as P of J plus Q of J plus W of I comma J minus 1. This is related to the weight. Similarly, in order to find the cost, it has been given by the formulas C of II equal to 0, where I ranges between 0 to n, and C of Ij is being given by the formula, that is W of I comma J plus minimum of C of I comma K minus 1 plus C of K comma J. And the root, the R represents the root. So R of I comma I is given as 0, and R of I comma J, the value that of K that minimizes, the value of K that minimizes this kind of the optimal binary search tree. So these are the things which you have to know, how to find W of I comma I, W of I comma J, how to compute, and similarly what is the formula related to C of I comma J, where I is not equal to J, and how to find R of I comma J, and so on. So provided these kinds of the values, you'll be using the tabular column. So what does this kind of the tabular column describes? That is, you'll be finding at every stage, that is W value, C value, and similarly R value, where the value of your ij ranges between 0 to 4. That is, you'll be computing W of 0, 0, C of 0, 0, R of 0, 0. In the next iterations, that is, you'll be finding that is W of 1, 1, and so on. So if you need to start from the first, that is how to compute W of 0, 0. So W of 0, 0, because in the previous slide, that is the assumptions are being made, that is W of I, I is equal to Q of I. And similarly, C of I, I is equal to 0, R of I, I is equal to 0, where I ranges between 0 to 4. So how to compute W of 0, 0? So W of 0, 0 is given as Q of I, that is Q of 0. So if you recall about the question that is being asked, that is P of 1 to 4 equal to certain values are being provided, and Q of 0 to 4 is being provided with certain values. That indicates the probability of successful search and the probability of unsuccessful search. So W of I, that is W of 0, 0 equal to Q of j. And what is the value of the j? That is equal to 0. So Q of 0 is equal to 0. In the question itself, it has been given. And that is how we can fill W of 0, 0 is equal to 2. That is W of 0, 0 is equal to 2. And the next thing that you have to find is C of 0, 0. So how to find this kind of the C of 0, 0? Because according to the statements itself, C of I, is equal to 0. The same thing is being represented. And how? This is how the value of the 0 is being stored in C of 0, 0. And R of I, because I value is equal to j, that is 0, 0. And that is how the value of the R of 0, 0 will be equal to 0. And the next thing is, if you need to find W of 1, 1, then what is the formula? That is W of I, j. Because I value is equal to 1. I mean, I value is equal to j value. The same values are being stored. So W of 1, 1 equal to Q of j. That is being given as Q of 1. That is equal to 3. So 3 is being stored. And how do you get this kind of the 3 value? In the question itself, it has been given. That is Q of 0 to 4. Q of 0 equal to certain value. Q of 1 equal to certain value. Q of 2 equal to certain value, and so on. And you'll be finding C of 1, 1, which is equal to 0. C R of 1, 1 based upon the formula. It is been given as 0. And then you'll be finding W of 2, 2, W of C of 2, 2, and similarly R of 2, 2. In the same fashion, we'll be finding W33, C33, since the value of your I equal to j. Both the values are same. I value is equal to j value. In such cases, you need to replace W of I, equal to Q of I, and whereas for C of I equal to 0, and whereas R of I is equal to 0. So these are the values which have been found at the initial stage. And when you need to compute W of 0, 1, that is, if you need to find W of 0, 1, because I value is not equal to j. And there is a formula that we have observed in your previous slide. That is W of I, j is being given as P of j plus Q of j plus W of I, j minus 1. So substitute, that is P of j. What is the value of your j? That is 1. So P of 1 plus Q of 1 plus W of 0, 0. Substitute the values of your ij respectively. So where you get the value to be equal to 8. And that is how W of 0, 1 is being calculated as value 8. And you need to calculate C of 0, 1. What is the formula related to C of I, j? That is minimum of C of I, k minus 1 plus C of k, j plus W of I, j. So you'll be finding C of 0, 1 by substituting the respective values, where you get the value to be equal to 8. And similarly, you'll be also finding R of 0, j. What does this R of I, j denotes? It is the value of the k that minimizes C of I, j. So here, the value of the R of 0, 1 will be equal to 1. And in the same fashion, you'll be finding W of 1, 2, which has the value to be equal to 7. C of 1, 2, that is equal to 7. And similarly, R of 1, 2 will be equal to 2. And you'll be finding the next values, that is W of 2, 3, that is 3. C of 2, 3, and R of 2, 3, C3, 4, W3, 4, and so on. And you'll be finding for the other kind of the values, that is W of 1, 3, W of 2, 4, W of 2, 5. And this is how your final value or being obtained. That is, what is the value of your the W00, and similarly, what is the value of your the W01, C01, R01, and so on. So these are the values which are being obtained using the tabular method for solving the optimal binary search tree. So what can you interpret related to the optimal binary search tree? That is, we'll be arranging the keys in such a way that is T04 will be the root, and T01, that is tree 01 will be the left child, and T24 will be the right child, and T00, which is the left child of your the T01, and similarly T11, T22, and as well as T34. So here, what can you understand is the word R04. What is the value of your the R04? Because the root has the value to be equal to 04. So R04, that will be equal to 2. That is second element and second key. So in the question itself, it is being provided what are the keys that are being provided with along with the probabilities and along with the successful search and as well as the unsuccessful search. So R04, it has been computed as 2. It indicates the second key, and R01, that is R01. So R01 is equal to 1, which indicates the first key that has to be placed. And similarly R24, that is the third element. The third key has to be placed at this kind of the level. And similarly R34, which is being kept as the 4, which is computed as 4. That indicates the fourth key. So if you arrange according to this kind of the order, that is a T04 which contains A2, that is the second element or second key which is being provided in the K. So hence the left subtree is T01 and the right subtree is T24. The root of T01 is A1 and the root of T24 is equal to A3. And the left and right subtrees for the T01 and T00 and as well as the T11 respectively. So the root of the T01 is equal to A1. So here what you have to understand is this is your R2 value, R04 value, and this is R01 value, R24 values, and this is your R34 values. So based upon values which are being stored in this kind of the tabular value, that is what is the value of your the R04, that is 2, and similarly what is the value of your the R01, that will be equal to 1, and what is the value of your R24, which is equal to 3, R34, which is equal to 4. What does this 1, 2, 3, 4 indicates is these are the keys, because n equal to 4, there are 4 keys which are present. So whenever we have the value or some value, something like a 2 is being present, then it indicates the second key which has to be present. So here according to this example, that is R4 is a root and R01 is a left child, R24 is a right child, and to the right of your the R24, the right child is equal to, that is R34. Since R04 is equal to 2, that is if has to be placed as the root, R01 equal to 1, that is the left child should be kept as the first key, that is do. And similarly, if you consider about R24 value, so R24 value will be equal to, that is 3, that is the third key that is present. And similarly R34, this is your R34 with the value to be equal to 4, indicates the fourth key. That is what we can say about the optimal binary search tree, how we can solve. So here one thing that you need to understand is about how to generate the values in this context. So how to generate the values? You need to understand about the formulas, because once you memorize the formulas, what are the formulas which are being used? The formulas which are being used to compute are, that is W of I comma E equal to Q of I, W of I comma J equal to P of J plus Q of J plus W of I comma J minus 1. So if you remember these kinds of the formulas, then it becomes easier to find the values in your tabular method for the optimal binary search tree. Because even in the case of the optimal binary search tree, which can be solved using the dynamic programming. And within the case of the dynamic programming, you'll be finding what is an optimal solution at every stage. So at every stage, you'll be finding what is an optimal solution. So here in the same fashion, you'll be finding at your first stage, what is the value, what is an optimal values that are being generated at the second stage, and so on. So if you need to find at the respective stage, its respective cost, weight, and what is the root, these are the formulas that are to be implemented. That is W of I comma I equal to Q of I, C of I comma I equal to 0, R of I comma I equal to 0, and whereas computing W of I comma j, which has been given by P of j plus Q of j plus W of I comma j minus 1. And whereas computing the cost between I comma j is been given by W of I comma j equal to minimum of C of I comma k minus 1 plus C of k comma j. In the same fashion, you should also find the root. So these are the values where we can find depending upon the formulas. Because at your stage 1, that is, you'll be finding that is a W of II, that is W of 0, 0, W of C of 0, 0, W of 1, 1, W of 1, 2, and so on. This is easy to find the cost or the weight or the roots at the basic level, at the stage 1. And coming to the next stage, at the second stage, that is, you need to find W of ij. And that is how you need to substitute the respective values of your the ij given the equation. That is W of ij equal to P of j plus Q of j plus W of I comma j minus 1, where you get the values. That is W01 you get C01 or 01 and so on. So once you fill all these kinds of your the cells by replacing the values of your I and j, these are the values which have been obtained. And to the next level, that is, you'll be finding the tree, that is T04 as the root, T01 as a left child, T24 as a right child, and so on. And that is how we can finish.